Hey everybody, welcome to Supplementary video 6.4 to 6.7. I know this is a little bit out of order, but I didn't really like where this fit compared to a few of the other video lectures and what we had going on in class. So this is why we're going back a little bit to chapter 6 and looking at those sections 4 through section 7. We're going to be looking at how cartilage develops into or is replaced or is involved in the ossification or the transformation towards bone, especially as you develop. So the first kind we're going to look at is intramembranous ossification. This is where you're going to have compact and spongy bone developing directly out of the mesenchymal connective tissue. Mesenchymal connective tissue is simply just undifferentiated connective tissue. Kind of think of it almost like a stem cell type of tissue. The flat bones of the face, most of your brain case, as well as your clavicles, are also going to be developing via intramembranous ossification. And here are the steps. Mesenchymal cells in the embryo. So you can see we're still dealing with an embryo here. They're going to gather and begin to differentiate, giving rise to osteoblasts. Those osteoblasts will be appearing together in what's known as an ossification center. Those osteoblasts are going to begin secreting osteoid, that matrix, which is going to harden as those mineral salts, calcium, phosphate, and things like that are going to be deposited on it, and that's going to trap the osteoblasts, as we saw in a previous video. Any osteoid that are near capillaries are going to eventually become the trabecular matrix and start to crowd into those capillaries, and it's actually going to influence those capillaries to differentiate into red marrow. But your superficial osteoblasts are going to eventually become part of the periosteum and begin laying down compact bone. Those osteoblasts then will differentiate into osteocytes, and the nearby osteogenic cells are going to replace those osteoblasts by differentiating into osteoblasts themselves. So here we can see the steps going A, B, C, D here, where we have these mesenchymal cells, those undifferentiated cells. We have an ossification here with this group of osteoblasts. Eventually, they will start secreting that osteoid. Those osteoblasts will be on the outside here. You do have osteocytes in the middle that are being trapped by that osteoid from that new bone matrix being laid down. Here we can see what it looks like where you have your trabecular matrix down here, the periosteum beginning to form here on the superficial ends of the bone. Eventually, you're going to have red marrow filling these cavities down here, and osteoblasts here forming part of your periosteum. The other way that bone tissue develops is through endochondral ossification. This is where bone is actually going to be replacing hyaline cartilage. So it's not actually coming from those mesenchymal cells, but it's going to be replacing that hyaline cartilage. So these are going to be responsible for forming the bones at the base of your skull, as well as your long bones. So you start off by having mesenchymal cells differentiate into chondrocytes. That cartilage model of the bone and the perichondrium is going to start to form. So you get kind of this very generic shape that the bone will eventually kind of look like, form of completely cartilage. That's going to form. You're going to have capillaries start to penetrate into that cartilage, and then the perichondrium is going to transform into the periosteum, the outer layer, and you're going to get the periosteal collar developing. You get what's known as a primary ossification center. Basically, this is where bone development is going to take place before birth. And then the cartilage and chondrocytes are going to continue to grow at the ends of that bone. And you'll get a secondary ossification center. So this is going to be where bones are developing after birth. This is going to be in areas like your growth plates. So the cartilage remains at those epiphyseal plates, otherwise known as growth plates, and at joint surfaces like your articular cartilage. So you can see here you have just kind of a generic shape that you start with as that perichondrium forms and that cartilaginous model. And as the capillaries penetrate, as matrix is laid down, you'll start to see that cartilage push towards the ends of the long bone. Eventually, that's going to leave you with just this epiphyseal plate, your growth plate here, and that's where the bone is going to continue to grow at that growth plate there after you're born. So you get these secondary ossification centers there, whereas initially you just had a primary ossification center. Okay. So we'll take a look a little bit more at what happens with those epiphyseal plates once they've formed, and once you're left with just those to be responsible for bone growth. Bones are going to lengthen due to the epiphyseal plates or the activity in the middle two zones specifically of the epiphyseal plate. So the most superficial, and I don't know that I should necessarily say superficial, but we'll just say it's the top layer of the epiphyseal plate is known as the reserve zone. This is going to be on the epiphyseal side of the epiphyseal plate here. So this is the side that's closest to the epiphysis in a long bone. And those cells are going to be responsible for securing that epiphyseal plate to the osseous tissue, to that bone tissue of your epiphysis. The second zone, one of the two zones responsible for bone lengthening, is called the proliferative zone. So you're going to have new chondrocytes forming. They're going to be responsible. They're actually replacing cells that we're going to see here in a little bit. The chondrocytes that are dying on the diaphyseal side. Sorry. The third zone, the other zone that is responsible for bone lengthening, is the zone of maturation and hypertrophy. Very long name. This is where cells that are formed in the proliferative zone are going to get pushed down into the zone of maturation and hypertrophy, and they're going to begin to grow and they're going to begin to mature. Eventually, they will get pushed down even further to the zone of calcified matrix. Here, you're going to have this matrix and these dead chondrocytes. They're going to be responsible for connecting your epiphyseal plate to the diaphysis portion. So you had your reserve zone connecting your epiphyseal plate to the epiphysis. The zone of calcified matrix is responsible for connecting that epiphyseal plate to the diaphysis. Then you have your proliferative zone and your zone of maturation and hypertrophy, responsible for forming new chondrocytes, those new cartilage cells, essentially, and allowing them to grow and mature. And as they do, they're going to be pushing cells um, further into that zone of calcified matrix. And so that they're going to push those cells down, and that's going to be responsible for lengthening the bone. Bones do also grow in diameter through modeling, and you also do get bone remodeling when you're going to be fixing old or damaged bone by fixing those. Usually, it's going to be the shaft, the diaphysis, but it could be oftentimes you may have a break around like the surgical neck of a long bone, and you'll get some remodeling there as well. Usually, that's going to be your osteocytes breaking down part of the medullary cavity and osteoclast breaking down part of the medullary cavity, and osteoblast laying new bone on the deep portion of the periosteum. So here you can see those zones of the growth plates and what's happening to the chondrocytes as we move down, starting with that reserve zone. Then you get into the proliferative zone and the zone of maturation and into hypertrophy, eventually into the calcified matrix where those cells are considered dead. One last thing we'll look at is the effects of exercise, nutrition, and hormones on your bones. Lifting weights, resistance training is actually the best way to increase bone mass because your bones are going to remodel in response to the stress that is put on them. And in the same way, they're going to remodel to the lack of stress that's put on your bones. So, if you're somebody that you're putting a lot of stress on your bones because you're lifting a lot of weights through resistance training, your uh, bones are going to lay down new trabecular matrix in those directions of that stress. And so it's going to make sure it's going to keep that bone strong, especially in that spongy bone. It's going to keep it strong in the directions of the stress. So you don't want to do just the same movements all the time and have the same direction of stress. You want to be able to incorporate different movements so you can get different directions of bone matrix getting laid down so that those bones can be very strong in that spongy bone. And if you aren't lifting weights, doing any sort of resistance training, those bones will actually take out that calcium. They'll take out some of that spongy bone because it isn't needed. And so you're going to use that calcium elsewhere in the body. Calcium, like we've mentioned many times, is necessary to build bones, but you do need vitamin D in order to absorb calcium in the small intestine. A lot of times, you're going to get vitamin D in response to sunlight, but most people these days actually don't even go out in the sun enough to make enough vitamin D. And so we'll actually fortify milk with vitamin D. So milk is a good source of calcium. So let's just put vitamin D in there so that when you're drinking milk, you're getting that vitamin D, and that can help you absorb the calcium that's also in that milk. Growth hormone is going to be human growth hormone or just growth hormone in general. GH is going to stimulate bone lengthening. And then other hormones such as thyroxine, testosterone, and estrogen are going to stimulate the production of bone matrix and make those bones grow larger, make your bones grow longer. Okay, so that is a quick look at how bone is develops either directly from those mesenchymal cells, or it can replace hyaline cartilage, as well as a little bit about a couple of things that affect bone lengthening and how your body can respond to different levels of stress.